So in this video now, we will be talking about the designs of the adsorbers and how they are applied in actual installations. So carbon fiber adsorber, in this setup over here, we have the solvent-laden exhaust air is coming inside. And the very first, it will have a pre-filter. And that's again for particulates. The gas will go inside and will try to condense out of it any liquid or any moisture that we can to get it. So we'll have a condenser where we will have, by the difference of the temperature, we will try to push down water or moisture out to leave only gas inside. Why do we do that? Exactly, because humidity decreases the retention. So if we can get away some of the moisture out, then we are increasing the capacity of the carbon. That's one thing. The other thing is also, if we can condense some of the water, we are actually condensing some of the VOCs. Because remember, the VOCs, they partition between the liquid and the gas. So while we're condensing water, we can also condense the VOC and get them in the liquid. So that means we are reducing the amount of them in the gas. Now, the VOCs are the one that we are treating with this one. So some of them will come out in the wastewater. Okay, so this is the wastewater here, and we can get that out. So we also have a system for regeneration. So you have here steam solvent mixture, and you can recover the solvent here. Here is the steam for the regeneration, and also cooling water, that's for the condenser. Any equipment sophisticated like this, you will have a control panel where you can control the whole thing digitally on a board that's also usually is connected to a computer that you can control in a control room for the whole factory. And then you will have your canisters of carbon. Look here, these are your carbon canisters where the adsorption happens, and then you can get your purified exhaust air coming out of the exhaust over here. And you can see that you have compartments, while one of them is being adsorbing, the other one is being regenerated. The cooling water that's how you do the condensation. The condensation depends on the temperature difference. So you put cool water to reduce the temperature, so you condense, and you let the others pass. Similar to, remember, method 18 or method 25? Let's watch the videos. Method 25, we had also this ice bath where the gas goes through to condense the water. Condense the water from the gas stream, and then you get the condensate out alone, and then the gas out alone. So rotary bed adsorber, this is a very interesting concept, which the adsorbent is being rotated all the time. So it's really like a circle. You see this circle here? This circle. So it's a rotation, and it keeps rotating. The carbon in it, sometimes it sees the gas that's polluted, and sometimes it sees the regeneration by steam or by hot air. And it keeps rotating. So the same part is going on. Now it's being absorbing. Now it goes to the heat, it's being regenerated, and then it's absorbing. So all the wheel, some of it is absorbing, some of it is regenerating, and it keeps going. Why this is easy? Because the gas is stationary, is going in one location, and the regeneration is stationary. So we don't have to keep switching between this bed is absorbing, this bed is regenerating, but the carbon itself is moving, and while it's moving, is being absorbing and regenerating at the same time. It's a very interesting concept. Fluidized bed adsorber. So in this one, fluidized bed meaning that it's the fluid inside can move everywhere. So in this case, we put the carbon inside a reactor. I just want to do the schematic for you. And then we have the air coming here. And because this is particles, so they keep flying. They keep flying inside. You get the idea? Imagine you have dust in a tube and you put air through it. What will happen in this dust? It will just turn around and it will cover the whole space. This is called fluidized bed. So this setup is called fluidized bed. The opposite is packed bed. The packed bed is where you have the things, they don't move. This is the difference between fluidized bed and the packed bed. So also another setup is the fluidized bed, where you get your air coming from one part, and then you have it go through fluidized, and then you get recovery, and so on and so forth. Finally, let's try to solve one problem where we wish to treat an airstream containing 0.005 mole fraction, which is 0.5%, 5,000 parts per million toluene, moving at a flow rate of 1,000 standard cubic foot per minute at 100 Fahrenheit and 1 atmosphere to remove 99% of toluene by cooling, condensation, and phase separation. To what temperature must we cool the airstream? So again, given is 0.005 mole fraction, which is 5,000 parts per million. We have the flow rate Q. We have temperature. Sorry. So we have the Q, we have the temperature. What's happening? This is T1, T1, and this is P1. And this is the removal efficiency, eta, 99%. And what we want to know, temperature, T2, that we can use to do this. To achieve 99% removal of toluene by cooling, condensation, phase separation, you need to reduce the mole fraction from 5,000 ppm to 50 ppm. It's 99%. So from 5,000, if you remove 99%, how much you have left? 50. How do you remember from the class when we talked about control equipment, that removal efficiency, how we calculate it versus retention and so on. Here is the step-by-step explanation. The initial mole fraction is 5,000. The target is 50. The partial pressure, P toluene, is equal to Y toluene times P total, where Y toluene is equal to 0.0005, and the P total is 14.7 psi. So multiplying 0.005 times 14.7, we get 7.35 times 10 to the power negative 4 psi. 0.0005 is the 50 ppm. That's 0.005 over 100. P total, that's atmospheric. That's 14.7. Yeah. The P toluene now it's 7.35 times 10 to the power negative 4 psi. So that's what we find out. Now we will use Antoine's equation, which is we covered last class, log 10 P equals to A minus B over T plus C. And we will go get, for toluene, we'll get A, B, and C from the appendix, from the table that I have for you in the slides. And then we'll substitute to get the target partial pressure of toluene, the 5 Pascal, and we'll solve for temperature. If you go to this equation and this thing, you will get that the required temperature to remove 99% of toluene is about minus 60 Celsius. So if you, just by changing the temperature to minus 60 Celsius, you are removing 99% of the toluene from this airstream, which is really amazing. If you think about it, you can just clean up by changing the temperature. So with this, we'll close this class, and then next class we'll talk about other technologies for the treatment of VOCs.